So we've been talking about solving the heat equation on an infinite domain. So you have heat equation, but x goes from minus infinity to infinity. And so using transform methods, we were able to show the solution has this form. So, just take a look at it for a second here. U hat of m, that's basically a type of Fourier coefficient. Now we're calling it the Fourier transform. And so here, U hat of m is we're calling the Fourier transform of u of x. And you should kind of decode what we're looking at here. What you should really see here is a type of projection formula where this integral is an inner product between our data. So capital U of x is our initial condition, our temperature when T equals 0. And e to the minus IMX, that's our basis. And so here we should really see the type of projection formula that's being normalized, type of projection, okay? And so we saw that this was the solution. And if we let T equal to 0, so right here, if we let T equal to 0, then this term disappears. And I'll have a T equal to 0 right here. And the whole thing, so I'll have a T equal to 0 right here. So this will be a 1. And this will equal U of x in theory. And when you let T equal to 0, we call this an inverse transform, but when you let T equal to 0, really what you should see is a Fourier series, basically. So here, U hat of m is our Fourier coefficient. Here we're summing the IMX, that's like cosine, there's plus sine. And so there's your Fourier series and then Fourier coefficient, but we're calling it inverse transform and Fourier transform. Because essentially, we can identify the function with its Fourier coefficients. Because if I know the Fourier coefficient, I can find U of x. And if I know U of x, I can find the coefficient. So yeah, we then had this theorem about the Fourier transform. And if the initial data was well behaved in a certain way, then we got these results about the Fourier transform. They're all important for just practical reasons. We need a bounded function. We don't want to deal with something that's exploding to infinity. Continuity is really a nice property to have. In particular, continuity, is required to apply Maclaurin series, Taylor's theorem. So if we want to do any approximation of U hat of m, having continuity is nice. Just in general, that's a nice property for our transform data. If U of x is our data and it's not very nice, well, its transform is nice in the sense that it's continuous. And then we have this oscillatory integral calculation, which also kind of gives us the result that if you clip the U hat of m, if you restrict its domain, instead of going minus infinity to infinity, you go minus capital M to capital M. Hopefully this tells us we're not losing too much information at the tails. So, one way of doing estimates, as I said, is to use a Mach series or Taylor series, Maclaurin series expansion. And for that, continuity is required. And so the Riemann-Lebesgue lemma gives us continuity, provided that, U of x, that integral absolute value of U of x is bounded. U of x is an absolute integral function. So yeah, here I just wanted to highlight mainly this aspect of it. What we can do now is substitute in for U hat of m. We can replace the first term, as a starting point, and then calculate that integral to get a large time estimate. So this is where we were last time. We were looking at the Dirac delta function, which is this really strange function, which I'm sure some of you have encountered. it's, formally defined in a lot of different ways. For me, this is, the definition that I always think about. People also think of it this way. And it's kind of this impulse function, this punch function, where at one single point, there's this huge impulse. I kind of think of it as if you have a big metal plate and you hit one spot of it, and that pushes out that metal plate. That's like, to me, the Dirac delta function, and you can emphasize, to me, it's almost like a magnifying glass in that sense. For each time the Dirac delta function is 0, it's magnifying that particular point of whatever it might be multiplied against. So the fundamental solution of the heat equation is that the solution to our beloved heat equation, for the infinite rod, x between minus infinity and infinity, where we have the Dirac delta function, this very, unintuitive, seemingly maybe not natural, maybe it is natural, I don't know. How do things happen in nature? So here, if we have the Dirac delta function as the initial condition, then we can show, using the transform and doing some math, that we get this, essentially it's a bell curve. That's essentially the Gaussian bell curve as the solution. So, the question is now, okay, so why do we call it the fundamental solution? So now here's why it's the fundamental solution. We now go back to our beloved heat equation on a finite rod, Dirichlet boundary conditions, and some initial condition f of x when t equals 0. So here, there's some comments about the continuity of the differential equation. We never actually required to be continuous in t all the way to 0. So here, for the solution, what we would like, though, is a continuous solution. And so here it'll turn out that that will be true of this solution. This is kind of a side topic that I didn't really go into that much. But anyway, using the method of images now, we can show, so what's the method of images? We're going to take this initial condition, which is defined on 0 to L, and then make an odd extension. So when we make an odd extension, then it becomes defined on minus L to L. So we do an odd extension of the initial condition, and then take that odd extension and do a periodic extension. And so now we have f tilde, our initial condition now is defined from minus infinity to infinity. And now we're pretending like we have an infinite rod problem. So check out this notation. So that's the periodic extension of the odd extension of f. And so we claim that the unique solution to this problem can be shown to be, this function here. So if we take a look at it, so we say, where's the fundamental part? So, what we should notice is this part, that those two expressions make up what we call the so-called fundamental solution. And, so this function here, or this PDE, seems to be some type of basis problem, in the sense of basis like a vector space, because it looks like I'm now able to write the solution of that heat equation for finite rod where we extended it. Like I'm writing it as some kind of, linear combination here, continuous linear combination. It's not a sum, it's an integral. And maybe there's some type of projection involved because we're multiplying in. So here what we do to find the solution that's on the next slide, I'll go back to here, we're integrating and we're multiplying by f here, the extended version. So that's what you see on the next slide. So that's why we're calling this the fundamental solution. We're able to write the solution to this heat equation for any, initial condition here, f of x, once we extend it appropriately, there it shows up with this fundamental solution part, which is going to always be there. If we change the initial condition f of x, the only part of the solution that changes is this part. Be careful of the notation. I'm using x bar because I didn't want to use x twice and I didn't want to use t. And so this is the only letter I could come up that we weren't really using. I didn't want to bring in another random letter. So that's just a dummy variable. What we have here is a function of x and t. So whatever x you pick will go in here. Whatever t we pick will go in here. And then, and of course down here. And then we can integrate. So yeah, I almost see this as some type of projection formula where you're getting information from the initial condition and then combining it. Maybe it's like projection and superposition. It's kind of all jumbled up here, just in an intuitive way of trying to understand what's happening. And so here's the fundamental solution. Maybe they're like projecting it and finding the solution or creating some kind of linear combination. I don't know, just, so that's why it's fundamental. We can kind of describe the solution now to the general heat equation in every case using this, what we call Gaussian kernel. That's the Gaussian kernel. Or heat kernel, I think sometimes people call it. So, we want to ask, so one question now to ask is, well, hold on, we solved this equation way back when, back in September or whatever, using Fourier series. And now you're telling me we have this other equation? And I thought you said the heat equation solution was unique. So what's going on? How do we resolve this solution involving the fundamental solution, so-called genuine solution, with our Fourier series solution that we know and love? And so now when we look at this, we recognize it instantly. Every part of it is very familiar to us. We know all about it. And, here's the coefficient. We know for the heat equation with trivial Dirichlet boundary conditions, we get a Fourier sine series. And so, here's our projection formula to find the coefficients. Here's the spatial part, decaying time term. So every part of this we know. How are these two related now? That's the question. And so, of course, deep in our heart, we hope they're equal, right? That's what we're all desperately hoping, so that life will coalesce and be a little simpler. And so, yeah, it does turn out that that is true, that the genuine solution involving the fundamental solution and the Fourier series solution here involving this Fourier sine series turn out to actually be equal. So single star and double star turn out to be equal. So that's what I say here. So that this genuine solution is equal to this series. And it has this continuity property that we want. So of course, the math is a little bit heavy lifting, but I give you the idea of the proof. I don't go into it too closely. So here, it says that by inspection, u of xt is a smooth odd periodic function of period 2L of x. I wish, when I typed up, it did it with so much confidence. And then when I look at it later, I'm like, wait, what? So I don't know, but I'm assuming that has to do a lot with the idea that the integral of a periodic function is, again, still periodic, So I know this part's periodic. I don't know about this other part. Is that periodic? Anyway, well, let's just accept this first statement here, that the genuine solution is smooth and it's an odd periodic function. So the idea of the proof is, the question we can ask, not even talking about the proof. Okay, so if this is the solution, my question is, what if we try and find the Fourier series of this function? If we restrict this function from 0 to L, can we try and find the Fourier series of this thing? So we want to try and write u of xt in this form. It's not quite a Fourier series because I'm now going to assume this coefficient is also a function of time. Because here, you know, for a Fourier series, we represent functions that are purely functions of x typically as Fourier series, right? You say f of x equals, and then you have a Fourier series expansion that only involved the variable x. The actual solution to the heat equation, technically speaking, is not a Fourier series, right? This is not, technically speaking, a Fourier series. It's only when we let t equal to 0, the e to the exponential term, you know, becomes equal to 1. And then this is a Fourier series when t equal to 0. That's a Fourier series. Okay, so we're going to try and get there, but we're going to start by assuming that u of xt has this type of expansion. And so presumably now I want to find Bn of t, and more than that, what I would like to show is, so hold on. So now what I would like to show is we would like to find Bn of t here. And what we would like to show is that Bn of t equals this function here, e to the negative n pi over L squared kt times B sub n. That's what we would like to show. If that is true, then we get, you know, the genuine solution up here, which we're trying to write in this Fourier series form, will be equal to our beloved Fourier series solution to the heat equation. Then those two things will be equal. Because this part with the sine n pi x over L, that part's the same for both of them. So this part here in our, starting out in our expansion, that part's common. So here by orthogonality, we get this formula using orthogonality. Okay, and you've got the t in there. Okay, so this is just using orthogonality. And now here's the trick, and I don't go into the details. What we do is we can create an ODE. We can show that this coefficient here, Bn of t, satisfies a particular ODE, and we do that by differentiating under the integral. So what does that mean? I'm doing a t derivative here. I do a t derivative, and then I bring that t derivative inside the integral. This becomes a u partial t, and now I know u partial t from heat equation, u partial t, that equals kuxx. And then you can do some integration by parts trickery and rewrite that. And so we can get a differential equation out of it. We can show this coefficient here satisfies this differential equation by using techniques very similar to what we did in the uniqueness proof, where you bring the derivative under the integral, take the derivative, and then use the heat equation. Replace, in our notation, we had v partial t, replace that with the heat equation equals v k times v partial xx, and do, a couple of integration by parts. And we can get this differential equation out of it. And then we can show the solution to the differential equation. And this is where we get the exponential term. One question is, okay, where's the exponential come from? In solving this differential equation, we get this form with the exponential term where c sub n is, some constant. And then with a little more work here, we can finally show that that constant, is equal to the Fourier coefficient. And so essentially the idea of the proof is to, try and write the genuine solution in this type of quote unquote Fourier series form, and then show that this b sub n of t is exactly equal to these other parts that we see in our formal Fourier series. And so that's kind of the way we resolve all of this theory. And you say, well, how do you, you said the solution was unique, but you have two different forms here. Well, they're the same. They just look different. You know, in theory, that's what's happening here. I don't know, it's kind of blowing my mind just a little bit. So I have last two slides, and you know, this slide was kind of the final sort of tying up some loose ends, introducing the fundamental solution, the Gaussian kernel or heat kernel, resolving it with our Fourier sine series, you know, and you can kind of similarly extend the theory in other, I think with the wave equation and stuff like that. So I wanted to talk about transform methods. So here, the question is, how do we solve this problem without using method of images to get this solution? Because we know how to solve the given PDE. We know how to solve it using separation of variables to find the, you know, formal Fourier series type solution. So we know how to do it with separation of variables, but what technique do I use to find this solution? You know, where did this solution come from? So that involves the transform method. So we talked about Fourier transform, and one of its uses is it helps us to solve PDEs. And so let me show you an example here, just a baby example. You know, we didn't go into this that much. You know, each one of these topics we could spend an entire semester on. That's the thing about it. It's a very deep subject. Okay. So here we assume some boundedness and regularity conditions on F so that the integrals are well behaved, because remember here at the end of the day, we typically are integrating from minus infinity to infinity. So for analytic considerations, math stuff, we need things to be well behaved. So this here, you know, ensures that f of x will essentially go to 0 as x goes to plus or minus infinity. So we'll make sure that f is a suitably decaying function, f and its derivative. So the very nice property of the Fourier transform is that we can take a derivative in x, we can take this x derivative, apply the transform, and that'll convert the derivative into a multiplication in frequency space. So here's another way. I wrote the same thing in our more traditional Fourier transform notation. Okay, so here, these two things are the same. I'm just doing two different notations because I want you to get used to it. Remember what the Fourier transform is. The Fourier transform is just the coefficient. It'll take a function of x and give us a function of m. Remember, that's what the Fourier transform does. So here, this hat here indicates the transform. So here, the Fourier transform of f prime of x, so think about this, this is a spatial derivative. That's an x derivative, is equal to, on the other side, we no longer have a derivative. So you should notice here, there's no derivative anymore. Instead, the derivative has sort of been pulled out and has been converted into this multiplication by I times m, where m is a real number. So now here, we're now in kind of the frequency space. Okay, remember here, the Fourier transform, this is a function of m. It takes input data f of x and puts out a coefficient, the coefficient we're calling the Fourier transform. So how is this helpful? Well, certainly in a PDE, where, for example, like heat equation, where we have two spatial derivatives, right? We have here two spatial derivatives. This transform property allows us to get rid of these two spatial derivatives. By applying the transform to both sides and using this transform property, I should be able to convert the PDE into an ODE, where the only derivative will be with respect to the t variable. And that's a fundamental strategy in math. Take the more complicated problem and make it simpler. So we take the PDE, make it into an ODE, solve the ODE in transform space, and then take that solution that's in transform space and inverse transform it back to our regular space and find the solution. So you'll show this property on a homework. It's not difficult at all. It uses integration by parts, and the fact that you can show the function decays as x goes to plus minus infinity. That's the whole reason we have this requirement here. These two things are, you get one from the other. And then using integration by parts, you can move the derivative from one term to the other. And when you take the derivative of e to the minus imx, you get an I minus im out of it. And then there's a minus sign from the integration by parts, and they cancel. So that's where this comes from. Okay, I'll let you do the details. It's really not difficult, but just sometimes the notation makes it look a little tricky. Just go slow. Okay, but it's pretty straightforward. I mean, this is really nice. This property, this decay property is very helpful. It kind of makes it work. So yeah, so what I want to do is take the Fourier transform of both sides of the heat equation. So in particular, what am I doing? So here, when you look at this, first I want you to just start by focusing on this part. So here, let me do this slowly. Just focus on the heat equation part. Okay. We start with the heat equation. And now what I'm going to do is multiply both sides by e to the I minus imx. So multiply by e, multiply both sides by e to the x or minus. And then integrate. I guess it's a minus. And then integrate dx integral minus infinity to infinity 1 over 2 pi. So starting from the heat equation, I'm multiplying all this junk and integrating. And then you get these, transforms on both sides. Yeah, at the end of the day, that's where you get that equation from. Okay, so if it's like, wait, where did this complicated looking thing come from? Well, it starts with the heat equation. What you should see is the heat equation first and foremost. Multiply both sides by e to the minus imx, and then integrate both sides minus infinity to infinity, multiply by 1 over 2 pi. So now we've rewritten it in terms of these transforms. And I've pulled the t derivative out, I guess. And here, I now want to use the transform property here to get rid of 2 of the x derivatives. So I'm applying the property twice. And so I end up by multiplying by im squared. And now you see there's no longer an x derivative here using this transform property. And so now you say, okay, so what? What's the big deal? Well, we've made the problem simpler. So now the problem is an ODE where there's only one derivative involved, the t derivative. And we know how to solve this ODE. We can show the solution involves this exponential function. Just like when you do separation of variables, we solve the t equation, right? We solve the t equation. We get something that looks a lot like this, right? We get g prime equals negative lambda g, right? Something like that. And that's where the exponential comes from in our separation of variables when we solve this ODE. Well, using transform methods, we get a similar type of ODE, and that's where the exponential comes from. And then finally, with a little bit of more work, we can actually show this turns out to equal the fundamental solution on that. So, and I won't go into those details. So trying to tie up some loose ends here, one question that always comes up is how is the Fourier transform related to the Laplace transform? for those who might be familiar with the Laplace transform. So the Fourier transform, I guess, is a special case of the Laplace transform. So if we have a function f of t for t greater than 0, where f satisfies, it's piecewise continuous, and it has this boundedness condition. Again, this is just so that the integrals make sense and stuff like that. Then I want to define the Laplace transform. So we use this fancy L of ft. So the Laplace transform is basically this integral transform. We talk about integral transforms. So this is the integral transform. And it looks very similar, but so here we're integrating from 0 to infinity. That's one big difference. And here e to the minus st, that's not complex. And then we've got our function ft. And so S may be complex here, but typically it's assumed to be real. And Laplace transform is used a lot in solving ODEs, so you might have come across it in an ODEs class. So the Fourier transform, so now if you say, well, what if I'm not going to 0? What if I'm going negative infinity to infinity? What if t is not restricted in this way? That's kind of when the Fourier transform, we can make the Fourier transform look like a Laplace transform. So now if I have a function that's 0 for t less than 0, right? So then we can show that the Fourier transform, it'll integrate from 0 to infinity, and its form will be very similar to the form of a Laplace transform. And in fact, the Laplace transform now is seen as a special case of the Fourier transform for the case in which you're taking the transform of a function that's 0 for t less than 0. So essentially what we're seeing now, the Laplace transform as a special case of the Fourier transform. And you can do the math to actually get from the Fourier transform to the Laplace transform. And this just shows you how to do that variable change that'll get you from this sort of Fourier transform version to the Laplace transform version. And yeah, and actually in the theory, the way we find the inverse Laplace transform is to actually now use the fact that we have an inverse Fourier transform. Yeah, so it depends on what type of data functions you're dealing with. One transform might be more preferable versus the other, depending on what type of function you're dealing with in the domain on X. And so there's kind of little differences here between these little things. All right, folks, that ends the discussion of our discussion of separation of variables, and all of the different PDEs. I now want to switch over for the very end, last, for 5 minutes today, and the last lecture on Wednesday, we're going to talk about dispersive waves. So dispersive waves is yet another different technique of solution. It's related to all the other techniques of solution, but it's a slightly different approach. In particular, I believe this is also related to Harvey's research area. And there's a project on dispersive waves. So let me stop here for a second and switch over to the other set of slides. Oh, so this is it. Does anyone have comments or questions? This is it. Forever hold your peace. Heat equation. Fundamental solution. All right. I know it's at this point in the semester, we're all just tired, right? So, okay, let me switch over to the other slides and we'll talk about dispersive waves for like 10, 15 minutes here. So now we finally end our discussion of PDEs with dispersive waves from section 14.2. There's so many topics in PDEs, and any one of those topics is something you could spend your whole life studying. Certainly that's what I'm doing, Harvey and all of the people that do PDEs. So here's the introduction to this different kind of method of solving wave equation. Or these types of second order PDEs. So for the wave equation, just to remind you, it was a situation where we had a string tied at two ends for this Dirichlet wave boundary conditions, and we have an initial position and an initial velocity. And the string could be plucked or struck, and you have, it starts vibrating and stuff starts happening in the x and t variable. And using separation of variables, we showed it had this formal series solution where, one big difference between the wave equation and the heat equation was the wave equation didn't have this decaying time component. Instead, it had a component that was a wave in x, which we were used to, but then it also had a component that was a wave in t, which we didn't expect. And the idea is that there's two waves when the string is vibrating. There's the actual string vibrating up and down, but if you track any single point on the string in time, it's drawing a wave. Its graph is also a wave. So we have this space wave and time wave. So inspired by this, we're going to try and come up with a new technique of solution. So inspired by this, we say, let's assume, just as before, a type of separation of variables, f of x times g of t, where the solution u of xt can be decomposed into a, these function of x only, function of t only. That's, a fairly big assumption. If we don't make that assumption, though, it's hard. How else do we solve this problem? Other techniques, other research has to be done. But certainly as a starting point, this is a good one. So here, however, we assume that the f of x function looks like e to the ix, where this is a generic waveform, right? We're thinking of this as cosine kx plus I sine kx. And it's completely inspired by the wave solution here. We have a wave in x. Okay, check, I got a wave in x. And the g of t, we assume, has this form. And again, think of this as a wave. Think of this as cosine omega t minus I sine omega t. And this is a wave in t inspired by the wave that we have, the wave that I have in the t variable that comes up from the formal solution of our wave equation. And so we say, okay, let's write it as an x wave times a t wave. And here we can put it together. And so this is now what we call a dispersive wave. Where we interpret that, as being this product of these cosines and sines. In this form, it's completely combined, right? It's cosine kx minus omega t plus I sine kx minus omega t. And we think of this. And so what's the solution technique now? Okay, so it's great. Well, as before, what do we do? We're going to take this, plug it in for u now on both sides. Come up with an equation, the exponential term will appear on both sides and we can cancel the exponential. And we'll get an equation that involves the k, x, I, omega, and t. And so here, if we can solve for omega, so k is the coefficient here. So we should be careful. K is not the coefficient. So we'll talk about, so K is not the heat coefficient. K is a new variable. That's part of the problem. Actually, I meant to mention with studying this dispersive stuff. So we should talk about, if we can figure out what K and omega are doing, then we're in business, essentially. So here, if we know what omega is, and if we can say something about K, then I've figured out, the form of this dispersive wave and theoretically found another solution. So here, this is a convention. So one question you might have, why do you use the minus sign? And so there's some notational convenience to that. Actually, depending on what type of PDE we're solving, for example, for non-wave problem like heat equation type, we actually would use this more generic form. And you see there's no minus sign here on the t variable. But specifically with regards to this wave application, the minus I omega t is intuitively helpful. It kind of makes everything fit nicer. So as I mentioned, please be careful. K is not our thermal diffusivity constant, whatever, from the heat equation. Okay, so this section of the book uses all the same notation, but in a totally different context, okay? And I think Haberman uses omega when Haberman does Fourier transforms, and now omega is not the same omega in Haberman's earlier treatment. It's not a spatial wave number. So yeah, so let me kind of introduce the dispersive wave and just talk a little bit about its anatomy and what are the terms and what do the variables mean. And I don't think we'll have time this time to solve a wave equation, but we'll do that next time. And as I said, the technique now is, it's not very difficult mathematically. Once we come up with the theory of it, is just now to plug in the dispersive wave into U and try and solve for omega and say something about K. So here, the wavelength of the space wave, the wave in terms of the X variable. So it's a space wave that's specifically with reference to this X variable. And so we know here, you know, e to the I kx, that's like cosine kx plus I sine kx. In either case, cosine kx or sine kx has a period of 2 pi over k, right? So this is the spatial frequency. This tells us, you know, after traveling a distance of 2 pi over k, you'll see one wave. So that describes the frequency in terms of space, or distance here. When I say distance, I mean with reference to the X variable. And our time wave, here again, when we say time wave, that's in reference to this T variable. And the fact that e to the I omega t, you think of that as cosine omega t minus I sine omega t. In either case, cosine omega t, sine omega t have a periodicity of 2 pi over omega. And again, that frequency would be a time frequency. That's the amount of time you'd have to wait to see one of those time waves. So we have what's called a temporal frequency, a time frequency, and a spatial frequency. Okay, so we want to use those things to define what we call a phase velocity. And I'll explain why the term velocity has been brought into it in a second. So here, velocity typically is distance over time, right? And here, what I have is a distance frequency, and I have a time frequency. So if I divide this temporal frequency by the spatial frequency, the number of waves per 2 pi amount of time divided by the number of waves per 2 pi amount of distance, then we get a distance over time quantity. And so here, the omega over k, we can now interpret this as some type of velocity. And so we call it a wave velocity, a phase velocity. It's, you know, a velocity that's somehow driven by the dynamics of the time and space interaction. Remember, that's what's difficult in PDEs, is we have two variables to keep track of, time and space. Is that why life is so hard? So it's the interaction of this time and space that here is this phase velocity that perhaps seems to be driving the wave. Again, we have this math analysis versus what's happening in reality. So now we can kind of interpret this a little more, you know, by attributing some value. So here I've factored out the k here in the exponent, so we can write this second term as omega over k, and we can think of omega over k now as this phase velocity. So when we look at this dispersive wave, we can read off two pieces of information. I can tell you the frequency number, k is the frequency number of the wave, you know, the space frequency, and omega over k is the velocity. And so here, when I look at a dispersive wave of this form, e to the ik times quantity x minus omega over kt, I can say, aha, that's a traveling wave with wave number k. So the k connects to the frequency on the x-axis. the more frequent it is, the more oscillations we have going up, above, and below, essentially. So the wave number kind of regulates that, the number of oscillations, how frequent it is. And then we can say, oh, and it has this wave velocity of omega over k. And so that kind of now starts to give this random dispersive wave thing more of a wave type structure, that, it has this kind of traditional frequency number that we talk about for our waves, and it also has a wave velocity. So now we make further assumptions on omega. If in fact omega is a function of k, the wave number, so I'm referring to this k right here. If the temporal frequency is a function of the wave number, then we have what's called a linear dispersive wave. So when you look at this wave, you should think now omega here is a function of k. You would replace this with some function involving the k variable. And so then this is what we call a linear dispersive waves. And for a linear dispersive wave, the phase velocity is purely dependent on the frequency, on the wave number, the physical frequency value. So here, if you look at the phase velocity is omega over k, and if we assume omega is a function of k, then the numerator will be a function of k, the denominator will be a function of k, so the entire phase velocity will be a function of k. And one more little, because I'm trying to work up to what's a dispersive wave. Okay, so here, if the phase velocity is not constant with respect to the frequency. So think about that the velocity is affected by the wave frequency. So maybe a wave with a really, big wavelength is maybe slower, and a wave with a really short wavelength maybe might be faster, or vice versa, I don't know. But it's the phase velocity is affected by the frequency. Then we say we have a wave propagation problem that's said to be dispersive. Think about what the word dispersive means, to disperse, right? So here, the wave number is driving the phase velocity. So the wave number is causing the wave to move, So this is, I guess, in that sense, it's dispersive. And now this omega term, the temporal frequency, acts as this between space and time. It's when you look at this term here, think of omega as relating, the relationship between, so I just wrote this now as t over k. You think about if omega is 1, how does that change? If omega is 2, how does that change? If omega is 1/2, how does that change? So here, omega is really kind of regulating, in some sense, the relationship between the numerator and denominator. In the numerator of the t variable, which represents time, and in the denominator of the k variable, which represents our space. So this omega term is relating space and time. And once we make this assumption, then solving for omega in the dispersive equation, if we can successfully solve for omega, then we can successfully find a solution. So here, let me just remind you, and then I'll stop. What we're going to do next time is take this dispersive wave, plug it into the PDE. And now if I assume this is a dispersive wave situation where omega is a function of k, I then want to just solve for omega. Once I solve for omega, I can plug it into, this form here, and we have the solution, a formal solution at least. So that's what we'll do next time. And here, spend a little time thinking about how this does have very wave-like properties. And it turns out, we'll show this, that omega of k will encode all the information about the PDE will be captured in the omega of k function, but not the boundary conditions or initial conditions. So I will continue this next time. I thank you for your patience. And I'm going to stop right here.